Hi, this is Nimla Rednam. In this video, we are going to start the topic cubes and cube roots. Before going into the topic, let's look at the introduction where they have mentioned a conversation between two mathematicians, Srinivasa Ramanujan and Professor G.H. Hardy. I want to show you a picture. This is a picture taken in Cambridge University of Srinivasa Ramanujan along with his colleagues. This in the center right here is Srinivasa Ramanujan, and here in the rightmost, this is Professor G.H. Hardy. I've taken this picture from Wikipedia. So, Hardy and Ramanujan, two great mathematicians who had complete opposite personalities. On one side, we have Srinivasa Ramanujan, who was inspired by goddess Namagiri, a man who saw divine in every mathematical equation. On the other side, we have G.H. Hardy, who didn't believe in anything that can't be proved, and hence not even in God. Ramanujan was all about intuition, and Hardy was all about logic and reason. In a true sense of collaboration, their vision for the future of mathematics, future of mankind, was so clear and so inspiring that none of the hurdles could hold them back. Their friendship had without any doubt turned out to be as pure and perfect as mathematics itself. During Ramanujan's stay in Cambridge University, he was admitted in hospital due to ill health. When Hardy came to visit him, he mentioned that the cab he took had a rather dull number, 1729. Ramanujan immediately pointed out that it was quite the contrary. It was in fact a very interesting number. It is the smallest number that can be written as sum of two cubes in two different ways. Srinivas Ramanujan was one of the greatest mathematicians of all time. If you are interested in knowing more about him, you should be reading up. A lot of material is already available in the internet, and you can also read this book, "The Man Who Knew Infinity," written by Robert Kenigal, right? And there's also a movie based on this book by the name The Man Who Knew Infinity. It was directed by Matthew Brown, released in 2015. You can watch that movie as well. It's very inspiring, and it really, reveals all the difficulties faced, because we are talking about a century before now. 1913, 1919, it was more than a century before, earlier to now, and how he traveled 5,000 miles away from home, and the great discoveries that he has made, like his formulae, the discoveries that they were able to prove later on, they're right now used even in understanding the black holes. So you can understand the significance that Ramanujan's contributions has in the field of mathematics. So with this great start to our topic, cubes and cube roots, let's go back to what we actually mean by cubes and cube roots. Like we have seen in squares, I told you that the word itself it starts from geometry, right? So you know what a cube is, right? And if you look at the cube, let me show you a 3D model. Now, what is a cube? It is a three-dimensional solid shape, right? So, as you can see here, I have the length is equal to its breadth, and in turn equal to its height as well, right? In that case, you end up with this 3D shape called a cube. Now here, what we are saying is, why do we call the numbers perfect cubes? Is that now if you have a cube, that means the volume is length into breadth into height, right? So here they have given a kind of interesting activity where you can see, if you have collection of unit cubes with you, you can check how many cubes do you need, unit cubes, to make the next big cube. For example, here this is a unit cube, right? And how many more such cubes do I need to make the next cube, right? So You can see here, this is a unit cube. So how many more such cubes do I need to make the next big cube? Okay. And it turns out that you need 7 more. So total 8 unit cubes will give you the next cube. And then how many more do you need? So if you actually have a collection of unit cubes with you, then you can play around with them and do this as an activity. I want to show it to you in some other video where I actually show you how to make cubes using a piece of paper using the net of a cube, right? That I'll show you in a later video. So that is one interesting activity that we can do here. So now coming to the list of cubes, like I told you in the case of squares, you should be thorough with at least 25 to 30 perfect squares. Same thing here. I want you to fill out this blanks over here and be familiar with all the perfect cubes up to 10 at least, and then preferably up to 20. So that sometime maybe if you have some conversation with your friend where someone says, for example, 5832 is such a boring number, dull number, you can tell them it's actually not a dull number, it is a perfect cube, it is 18 cubes, so on, like, and it will be useful in solving sums as well. So preferably I want you to be thorough with at least 20 perfect cubes. Okay, so this is about the introduction that they have given. Now if you remember, in squares we have seen that the ones digit gave us a clue whether the given number is a perfect square or not. Can we do that in the case of a cube? Let us check that out. So what did we have in the case of a perfect square? We checked the ones digit and we saw that 1 square, 2 square, 3 square, everything was giving us only a few possibilities in the ones place, right? I'm writing the squares here just for quick recall. So 3 square gave us 9, 4 square gave us 6, 5 square gives us 5, 6 square gives us 6 again, 7 square gives us 9, 8 square gives us 4, 9 square gives us 1, and then I have 10 square which gives us 2 zeros. So I told you it's even number of zeros for a perfect square, not just 1 0, even. From this we saw that we concluded that if a number ends with 2, 3, 7 and 8, we can say that it is definitely not a perfect square. If it ends with one of these, then we have to investigate it further, right? So now in the case of cubes, let us see what happens. If I have one cube is ending with 1, 2 cube. When I say cube, we are talking about the number 2 multiplied 3 times, right? It will give me 8, right? 2 cube is 2 into 2 into 2, 8. 3 cube is 27, and that means it is ending with 7. 4 cube will give me 16 4 64, so it ends with 4. 5 cube is ending with 5. 6 cube is ending with 6. 7 cube, I'm not actually doing the multiplication here, I'm only checking the ones digit. 7 sevens is 49, 9 sevens is 63, so it ends with 3. 8 cube is ending with 2 because 32 and 8 fours is 32. And 9 cube is ending with 9. And 10 cube will have 3 zeros, right? So you can see here I have a 1, 2, 3, 4, 5, 6, 7, 8, 9 and a 0. So all the entire spectrum is covered in your ones digit. So I can't do this check when it comes to cubes, that is checking the ones digit and trying to rule out some of the possibilities. So that can't be done in case of perfect cubes. Next, if you remember, we looked at prime factorization. Now that is going to work because when I say a cube, I am talking about the number a being multiplied 3 times. So in the case of squares, we group them as a group of 2. Here we will be grouping them in groups of 3. So first the given number has to be written, you have to do the prime factorization and write it as product of prime factors. And then if you can group all the prime factors as group of 3, then it is a perfect cube. If not, you can conclude that it's not a perfect cube, and you can make it a perfect cube either by multiplying, that is filling out these whatever is insufficient in the group, or taking it away by dividing it by that number, by that factor. That is how the questions are going to be in the case of cube, right? Now they have given certain interesting patterns. Okay, I want you to look at this. Just a couple of patterns they have mentioned here. Now they're saying that all the cubes can be written as, now I'll be solving these, try these questions in the next video. All we need to do is find the ones digit, okay, which is very straightforward, right? So in the next one, they're writing the given, they're writing any cube, perfect cube as sum of consecutive odd numbers, not starting from the beginning like we've seen in squares, but it starts at some odd number and then you write, like if it is 5 cube, I am writing 5 consecutive odd numbers. However, he didn't say anything about where do I start these 5 consecutive odd numbers. So what I have observed here is, if you look at the first odd number, okay, 1 cube 1 is pretty clear. Now for 2 cube, I'm starting with 3. If you look at that, 2 can be written as, the base of this can be written as 2 into 1 plus 1, right? Similarly, if you notice, if you look at 7, sorry, it's not 2, I'm talking about 3. 3 can be written as, that is, this sum is starting with 3. So I'm interested in, is there any relation between this 3 and the base on the RHS, right? So here 7, I'm interested in 7. 7 can be written as, now look at this base, 3 into the number before it, 2 plus 1. Okay, so far so good. Let's check 13 also. Now 13, can I write it as, the base here is 4. So 4 into 3 is 12 plus 1. It's working here as well. And what about 21? If I look at 21, the base is 5 here. So 5 into 4 plus 1. So you can see that it's working. So, and then you, starting from 21, you're going to write the consecutive 5 odd numbers because the base here is 5. So when they ask 6, I'm going to start with 6 5 31, 30 plus 1, 31, and then go on for 6 consecutive odd numbers. Similarly, 8 and 7 as well. Now here there's another pattern that they're asking us to check out. If you take the difference of 2 consecutive perfect cubes, they're saying that it's always 1 plus 2, this pattern where I have the 1 plus, and then I will have product of these two bases 3 times, right? This is actually an identity, a cube minus b cube, which once you have the identity, this will become very obvious to you. But for now, we are going to use this pattern to check these 4 values. Okay, I'll be doing that. And the observing patterns like this is important because a lot of information is revealed. Once you see a pattern, then you can move on. That is how a lot of theorems were actually proved, right? You look at a pattern in numbers and then you see maybe it holds true for any number, then you prove it, and then we use it in our applications, right? So it is important to develop this habit and culture of observing patterns in numbers. So here I have prime factorization. We are already familiar. Only thing is, here I am going to be grouping it in groups of 3 because we are talking about cubes. Smallest multiple, that is a perfect square, what should be multiplied to the given number. This also will be doing it. You can go through the solved examples and all the try these questions and everything. I will be showing it in the next video, right? And after this, I have same thing here. I have to check whether these are perfect cubes or not. And then even the second exercise is very brief. They just introduce the cube root. This is the symbol, just like we had in the case of square root, which is the in a way an inverse operation of squaring a number. So if here, for example, I have 2 cube is equal to 8, then I can say that cube root of 8, this is the symbol, is equal to 2. One thing you need to notice here is in the case of square root, we had plus or minus as two possible solutions, but we only looked at positive value. Here, negative value is not possible. For example, if I take minus 2 and multiply it 3 times, I will be getting minus 8, which is not the same as 8. So, cube root of 8 will have only one solution, which is plus 2. Okay. So, that is about finding the cube root again through prime factorization. Okay. So, same thing we are going to be doing even here. And that is all we have for our sixth chapter, which is cubes and cube roots. All the sums I want to cover it and finish it in the next video, both the exercises 6.1, 6.2, along with try these questions and think, discuss and write. Coming to the solved examples, I want you to try them. They're pretty straightforward, and we have already done so many numericals on prime factorization. We'll be doing the same thing. Only thing is we'll be grouping them as group of 3. Another thing I want you to do is, like I mentioned, the activity where you have these cubes. Okay. If you have any collection of cubes available to you in terms of blocks, I try to demonstrate using Lego blocks, but I realized that they are not cubes, perfect cubes actually. It's kind of a cuboid shape. So I will be making cubes out of paper, and I'll try to show that. If you have any cubes available, you can do this activity. Try to see how many more cubes have to be added to this cube to get the next cube, and so on. Right? That will give you a sense of visualization of what we mean by a cube, and why is, if one cube is one and then the next cube is so far away, and then it's, increasing by a very large, the gap between two cubes, consecutive cubes, goes increasing much faster than the squares, like you've seen. So I want you to try that activity as well. So that's it for now. In the next video, let's finish this chapter, solve all the numericals and finish this chapter.